Okay, welcome back, and now let's connect differentials with linear approximations. Okay, so let's start with this. So remember that differentials can be used to estimate the change in the value of a function with a small change in x. Okay, so now consider the function f that's differentiable at a point A. We've talked about this before. Okay, now suppose the input x changes by a really small amount, right? Just a small amount. Then we're interested in how much y changes from A when the point, well, we want to know how much y changes, okay? If x changes from A to this, so if x goes from A to delta x, right? So there's the change. So we go from A to A plus delta x, okay? Then the change in x, right, is just delta x. So this is the change in x, also denoted by delta x, right? But we're talking about a small change in x. Okay? Now the change in y then is given by what? Okay, so what's the change in y? So the change in y is given by what? It's going to be f of A plus delta x minus f of A, right? And so instead of delta x here, let's use delta x, okay? Now, instead of calculating the exact change in y, it's often easier to approximate the change in y by using linear approximations, right? For x that's near A. And so when we use the linear approximation, we can approximate f of x by using L of x, right? So f of x, or we're going to use L of x. So L of x is equal to f of A plus f prime of A times x minus A, right? We saw that before. So, if dx is small, what does that tell us? If dx is small, then we can say, so if dx is small, then f of f of A plus dx, right, is approximately equal to L of A plus dx, right, which is equal to f of A, right, plus f prime of a times x minus a minus dx. Or no, that's not right. No, that's not right. It's, hold on a second. F of A yeah, oh, sorry. So, it should be A plus dx minus a. That's what I was writing. Okay, so again, I'm just putting in the values here. X, so this is x, right? This should be, yeah, that's right. Yeah, that's right. So here, a plus dx, right? So this is going to be approximately equal to L of a plus dx. Right? And L of a plus dx equals a, and then of course, this goes here. And then of course this cancels with that, and we end up with f of a plus dx is L of a plus dx, which is equal to f of a plus f prime of a dx. Okay. So now what do we do with that? Well, let's go further. So if this is true, right? So if dx is small, we have this, but now let's subtract f of a from both sides. Okay? So if we subtract f of a from both sides, then we get f of a plus dx minus f of a is going to be approximately equal to L of a plus dx minus f of a, right? Which is then going to equal f prime of a dx. Okay, and so that just follows from subtracting f of a from all three, from all of them. So now, in other words, what we're looking at here is the actual change in the function f, right? That's this, f of a plus dx minus f of a, right? So the actual change in f of x in the function f, if x increases from a to a plus dx, is approximately the difference between L of a plus dx and f of a. Where L of x is the linear approximation of f of a, as we talked about before. And so this difference is equal to f prime of a dx. So now, here's the summary. So, notice what we get here. This, by definition, is delta y. So delta y is equal to f of a plus dx, not bx, minus f of a, which we're saying is approximately equal to the linearization of the function minus, or the difference between them, and the function f of a, which is equal to f prime of a dx. Well, what is that equal to? I erased it, but what is that? We talked about this already. This is equal to, by definition, dy. So therefore, we can use the differential dy is equal to f prime of a dx to approximate the change in y. If x increases from x equal to a to x equal to a plus delta x. And that's what we're saying here. If x goes from a to a plus some small change in x, then we can estimate or calculate or evaluate dy by using that equation. Okay, so let's stop there and we'll come back and we'll do some examples. Have a great day.